Hey, general math. We have combinations today, 10.3B. Excuse me. So combinations are when we select from a group of items, um, but unlike permutations from 10.3A, the order doesn't matter. So let's say we're looking at the fridge, right? And we have, let's see, our example is an apple, orange, and a pear. We get to pick two of those fruits to take out for lunch or to eat for dinner or whatever. We get to take two of them. It doesn't matter if we pick out the apple first and then the orange, or the orange and then the apple. We're still just going to have an apple and an orange to eat for lunch, right? So we can pick out two fruits, but it doesn't matter what order we pick them. So how many different combinations of fruit could we have? We can see there are three combinations of two that can be drawn from this set. You can have an apple and a pear, an apple and an orange, or a pear and an orange. And we use a formula for this. So the formula for combinations is represented as N choose R. So on 10.3A, we had N, P, R. Now we have a C for combinations, and we're still using factorials. So remember, like, the factorial of 4 would be 4 times 3 times 2 times 1. So we have the factorial of n, so that's the total amount of options, and then n minus r factorial, and r is how many you get to choose. Again, we have a reminder up here. The difference here is that we also multiply by r factorial. So in the example above, there's 3 different fruits. We get to choose 2 of them. So the total number of n, right, the total number of fruits, we do 3 factorial over 3 minus 2 factorial, and then we finish it off with a times 2 factorial because our r was 2. So on top, we have 3 factorial, 3 times 2 times 1. On the bottom, 3 minus 2 is 1. So 1 factorial is just 1. And then 2 factorial is 2 times 1. Let's cross off a 2, a 1, a 2, a 1. What's left over? 3 divided by 1. We have 3 different combinations. Or you could just plug this whole thing into a calculator. Next example, we have 7 different colored Skittles in a bag, and we can choose 4 of them, right? So we have 7, we're choosing 4, so we're going to write that as 7 choose 4. 7 factorial is going to go on the top, and then 7 minus 4, n minus r factorial, so that'd be 3 factorial times r factorial, that's 4 factorial. So we have 7 factorial over 3 factorial times 4 factorial. Personally, I think it helps to list them all out, and we are going to cancel 4 times 3 times 2 times 1 with this 4 times 3 times 2 times 1 up here. So what's left over? 7 times 6 times 5 over 3 times 2 times 1. Plug those into a calculator, and we have 35 different combinations. We can see another example down here. We have 11 shirts to choose to pack for vacation. How many different combinations can you choose? Right, so it's a little different than when we're wearing the shirt, right? Because we have 11 shirts and we're not wearing them, so it's not like you can't pack something right in the wrong order. We're just taking those 11 and we're putting seven of those shirts into the suitcase. It doesn't matter what order we're putting them into the suitcase. So we're going to do 11 factorial. There should just be 1 exclamation point there. And then 11 minus 7 factorial times 7 factorial. So we have 11 factorial over 4 factorial times 7 factorial, and we get, after canceling right here, 333 combinations. So to get from this point to this point right here, I see that we have 7 times 6 times 5 times 4 times 3 times 2 times 1 on the top and the bottom. So I'm canceling those out, and we just have 11 to 8 on top and 4 to 1 left over on the bottom. Big takeaway, big difference from 10.3A, which was permutations. For permutations, repetitions are not allowed, and order does matter, actually. And for combinations, repetitions are not allowed, but order does not matter. I will change this.